All right, everyone. Hello and welcome to another video on deep learning. This one's going to be about backpropagation and recurrent neural networks, and we're going to keep it under 15 minutes. So if you haven't learned about artificial neural networks or don't know about recurrent neural networks, I suggest you check out the first videos on those topics. This one's going to be concerned primarily as kind of a second part of the series of recurrent neural networks, where in the first part we did forward propagation. This one's going to be concerned with the back propagation and more specifically kind of getting those trainable parameters and getting the gradients that we need to train our model. So let's dive in. From the last episode, you'll recall the unfolded RNN architecture. In this case, we're using 4 sample time steps. We have 3 trainable parameters, our shared weights, U, W, and V. And then we also have our hidden states right here, sharing information across time steps. Some important equations we have from forward propagation. We have the hidden state equation, which is just the hyperbolic tangent of the concatenation between the input vector times the input weight plus the weights vector times the hidden state from the previous time step. We also have applying the softmax function on the output of the hidden state times the output vector, output weight v, and we're applying the softmax function there to get a probability distribution for our classification, or just a classification vector. We're also going to have a loss function. In this episode, for backpropagation, we're going to assume cross entropy or the log loss function. You can use whatever mean squared error or whatever you're using. It's fine. You're just going to have to use that different derivative there and make sure you substitute it out for the one we're using in this video. Lastly, we're also going to use the nomenclature ZT to abbreviate this V times HT term that exists in the softmax function. On the right-hand side, we have our U, V, and W shared weights, the gradient descent equations for each of those weights, and we're going to need to be finding the gradients, or actually in reality, they're going to be derivatives of delta L, delta V, delta L, delta W, and delta L, delta U. And so if we're starting with the easiest first, we'll start with a V, and also just more logically, we're going to start from the top of the loss and go down. Let's try to find delta L, delta V. So equations already, as if I haven't reminded you enough. We're going to be using this softmax function, and we're also going to be using this ZT function right here. So to find delta L, delta V, obviously we do not have that expression defined explicitly in terms of V. The loss function is defined in terms of the output vector y hat I. And so we're going to have to use the chain rule, to kind of expound and break this out into multiple derivatives. So we're going to have this delta L, delta Li, delta L, y hat I times delta y hat I over delta zi, and then delta zi over delta v. And so let's start out by finding this first one right here. What we're going to do is take the cross entropy function. This is the log, or otherwise known as the log loss, and we're going to take the derivative of that with respect to y hat I. And it turns out, you can look it up on another video. I don't have that math right here, but you can take my word for it. This is that derivative, yi over y hat I. And you'll notice that this yi, just in case you aren't familiar with the deep learning nomenclature, this is our target output, and the y hat I is our predicted output, or the output that our model gives us. So this is an important distinction to realize. Next, we're going to find delta y hat I with respect to delta zi. This is actually a little bit more involved of a derivative to find, not so simple. It actually involves taking the derivative of a vector, so we're going to invoke some vector calculus. I won't show that math in this video, but if you are interested in understanding how I came about and derived the derivative, I have another video on this that I'll link below, and you can watch that one to see the full derivation. But basically, in short, before this is going to be the final derivative. It's going to be in terms of itself, actually. But it's important to note that there's going to be several cases. There's going to be 2 cases in this case. But whenever you're taking a derivative of a vector with respect to another vector, you're going to have to take the derivative of the vector at every single point, in every single direction. And so in this case, you're going to have to take it for many different values. And so when we get this final expression of the softmax derivative, This right here is the Kronecker, what we call a Kronecker delta. A fancy way of just saying, okay, it takes 1 when I is equal to k, and 0 when I is not equal to k. So just has a binary, takes binary values dependent on certain cases. So that's the softmax derivative. Now what we're going to do is we are going to multiply. We're going to multiply out, actually, before we do that, what we're going to do is then take this first expression and take this second expression and multiply them together to kind of clean everything up and get some a little bit more, see if we can get a little more simplified form. So this is that first derivative, and then we're going to multiply by each of the second derivatives in that in the two cases. And so we're going to start with the first case, I equals k, and take that first derivative and change these i's right here to k's for that first case, because it's the specific case where I equals k, and then multiply them out. Turns out you can cancel out of these y hat k's and end up with this just negative yk plus yk times y hat k. And then we'll move on to the case where I is not equal to k. So in this case, we'll take this original expression from here and then multiply it by that summation right here of all the values where I is not equal to k. And turns out you can cancel these two yi's, and after canceling, you get this nice, neat little summation here. Now, what we need to do next is actually get an expression for all of the values of i's. So we know when we're doing this a total expression here, we want something from all value I to t, not just for a subset of i's. And so for that matter, that's why we're going to need to concatenate this expression with this expression so we get all the values of I. And so when we do that, take I equals k plus all the values where I was not equal to k, it turns out we can do some interesting simplification. If you'll notice here, this term has a yk and this term has a yk. We can actually take that out of the expression using some algebra, and we're left with yk plus the summation of all yi's from where I is not equal to k. And by definition, we can actually just lump this into the summation and just have it be the sum from I equals 0 to k, so for all values of I. And if you know what the value of yi is, it's the target value, you'll know it's this matrix where it's all zeros except for 1, the value we wanted to classify into. And so if we take the sum of this vector here, we just get 1. And so by definition, we can actually just sum all this and we get the identity. And that actually leads us to be able to simplify the expression in this nice two-term expression, negative yk plus y hat k. Very simple there. That's nice. So then we can plug that into our initial expression for delta L delta V into these two terms and substitute in, and we get this expression. And this expression is actually just a simple delta Z delta V is just going to be ht. If you recall that derivative is very simple, right? This is the original expression. Taking the derivative with respect to V gives us this constant ht right here. And in this case, it's going to be hi. So this is actually going to be the outer product, since we're taking the product of two matrices. The outer product is otherwise known as the element-wise product, or the Hartman matrix. So keep that in mind. So this is our final expression for delta L delta V. Next, we're going to move on to delta L delta W. Now, this is actually going to be a little bit more involved of a calculation, and it's going to require a couple extra steps for us to get to the right answer. So we're going to need to use this same expression. You'll notice that in every single of the derivatives, we're going to have these two expressions because obviously we're trying to find the derivative of the loss, and we're trying to backpropagate towards those other parameters. So we can't. These are kind of like, we can't bypass these gradients here. So this expression will come in handy and be very useful, and we can just keep plugging it into those two terms. So what we're going to focus on is getting these two terms. But before all this, I kind of want to take a step back, and we're going to have to take a different approach for delta L delta W. Instead of just going and doing a general approach like we did for delta L delta V, let's do an approach where we start with a first loss function and then work our way up. Because if you'll notice and kind of take a look at the unfolded version, if we start with here, this is actually going to be, we're going to have to go through here, and then here, and then here to get all three of the weights and how they're affecting this loss. Whereas if we start with here, well, we'd only have to get one right here. Or actually, we'll start with this one and just get one. But, you know, it's also important to note that when we did delta L delta V, we're not actually backpropagating through time, because when we look at V, v only influences this loss function. This v doesn't influence this loss function. It's just this v, and they're going to have the same weight. So when we're doing that backpropagation, we didn't actually have to backpropagate through time. That's why it was so simple. With the weights parameter, we're actually going to have to backpropagate across the hidden states through time, which is going to give us a little bit more extra complexity. So kind of looking back at that, let's start with delta L, delta W, delta L1, delta W. And we can break that out right here. And we'll notice that delta Z, delta 1 is just V. Then, so we have this expression right here. Now we take delta H1, delta W is going to equal this long expression here. This expression is just the expression for the derivative of the hidden state function, the tan H function, really. This is the hidden state function. And we're just taking the derivative of this. This is that derivative. And so we can get this term right here. Now it's important to see that for delta L1, we have this hidden state HO. This hidden state, if we go back to the unfolded architecture, is actually just like a starter hidden state that we initialize some values. And it's not a real hidden state, but it's there just to make things programmatically simpler so we can have matrices of the same size across all hidden states. So going back to the calculations here, now we have our expression for delta L1, delta W. That was pretty easy. But now let's go on to delta L2, delta W. That's going to be a little bit more involved. So you'll see we can break this out right here, but we get H2 in terms of W. Well, if we look at H2, and I'm going to go up here, H2 is not just in terms of this W, but it's in terms of this W as well. And so you can't just change this one and expect to change. Like, you have to change both of these and see how both of these are changing in order to get the optimal way to change it. Okay, so to find that, H2 delta W is not just a simple expression. It's not explicitly defined. It's actually defined in both ways. And if you look right here, we're going to see that it's defined not only explicitly here with a function of W, but H1 is also a function of W, so that we have an explicit definition and also an implicit definition. And so when we take that derivative, we're going to have an explicit part and add it to that implicit part right here, which is the derivative of then H1 and H1 with respect to W. So in the explicit version, we just treat H1 right here as a constant and then just take that derivative as if H1 was a constant. And in the implicit version, we actually treat it as a function of W. So this is our expression for H2W, and we tack it on to substitute for this term, and we get our entire expression for delta L2, delta W. And so let's find delta L3, delta W, and see if we can find a pattern once we do this. So delta L3, delta W is going to be even more involved as well, because now we not only have it implicitly defined as from 1W, we have implicitly defined from 2 W's. And so here we have H2W, that's 1 that we have to add in, and then we also have H3, H2. And so we're going to have to actually have a lot of extra explicit definitions here. So just not just this one, but this one as well. So this is the explicit definition for H3, delta W, and then this is the implicit definition, right? And in the implicit definition, we have the explicit definition for delta H2, delta W, and the implicit version for delta H2, delta W. And so right here, I want to take a step back and say, okay, do we notice a pattern from this one to this one? And I think if you want to take a second to pause and look at it, you'll come to the conclusion that, we see these terms here kind of stacking up, right? We're going to need to take H3, H2, delta W, right? And then we're also going to have these explicit terms, H3, H2, H1, right? And we're going to have to add those on each time. And so if we just take that first part I mentioned with the multiplication of breaking it out using chain rule, we can see we can break this H3, H1 into a product of the two, which is then you can be defined using that pi notation of just multiplying delta HM over delta HM minus 1. And we can substitute that product right here and just put the delta HK plus, which is the explicit definition of K, as the on the end over here. And what we're going to be doing is we're going to be summing from K equals 0 to 3. So we'll have a nice summation here where, you know, each of these is going to be added on each time we sum here, here, and here. And then, not only that, this is just for delta L, delta 3. We've simplified and made a nice, more general expression, which is nice, a little bit more compact. But we only have L3 here. We have to sum L2, L1, as many loss functions as we have across each time step. So summing across all losses, we have to add in another summation here. So now we have a nested summation. And so this one is summing across the time steps for each loss. This one is summing across each loss function with respect to W. And then I also want to kind of more simply define this explicit derivative here. So if we take that hidden state function, that's tan h of this stuff right here inside, we can see that we get the derivative being this weight matrix multiplied by the derivative of the hidden state. Actually, this is the whole derivative. But you'll note that this is actually not just a scalar value, this is a matrix, and that's because we just took the derivative of the hidden state was a matrix, we took the derivative of another, well, it's a vector, we took the derivative of that with respect to another vector, so that gives us a matrix, and it's also known as the Jacobian in linear algebra. If you've taken linear algebra, this is kind of the direct application here. The other thing to note is this term right here. We can take, okay, we have hk plus over delta w. This is that explicit definition where we're treating the weight, in this case in the weights, we're treating this as a constant, and so we can take this this expression right here. And so we can substitute this right in here for this type of thing right here. And so we can get a final combined expression for delta L, delta W of these two nested summations, this product notation, and the element-wise product of that explicit derivative right there for each k. Also, you're wondering, okay, what about delta L, delta U? It actually turns out we can save ourselves a lot of time, and it's pretty much the exact same process, except this thing on the end changes. Everything else stays the same. All this stays the same except for this, and all this is going to change too is instead of taking that derivative, you'll go up here to hk. Instead of taking derivative with respect to w and getting this, we're taking it with respect to u and getting this boy right here, which is the xk. And so in this case, we can call it, I will actually change that's wrong. It needs to be xk. So that will be xk. And so that's a nice little wrap up of delta. We found delta L, delta W, delta L, delta V, and delta L, delta U. And so we have our three derivatives that we can then use for gradient descent. Now, one last thing I want to point out is, do you notice anything problematic about these expressions? Well, if you didn't, I did. And this is, one thing to call out here is that we have a summation nested inside of a pi product nested inside of a summation nested inside of another summation. And so you can see that as the gradients multiply, as we get more time steps, the gradients are going to increase by a large amount. And this is going to be not only computationally expensive, it's also going to lead to a problem of vanishing gradients because each of the gradients are less than 1. If you multiply something less than 1 by many times, to multiple times itself, you quickly get to 0. And so what we're going to see is the gradients trend towards 0, your learning falls towards 0, and your model doesn't train and it can't converge. And so that's one of the big problems. The other big problem is that even if your model does converge, what we start seeing in these RNNs with multiple time steps is that with a little bit longer sequences, you tend to lose information from the beginning. And that's because the gradients in the beginning are obviously become so small that the model can't really learn from them. And there's actually two solutions to this. The first solution, truncating gradients, prevents the vanishing gradient problem, but it doesn't help too much with that long-term context recollection problem, right? The problem where it doesn't recognize, it doesn't remember patterns, or it doesn't remember data from the very beginning of the sequence. So let's say you had a long sentence, it might forget words that came early on in the sentence. And the way we get around that is actually a modern solution is to use the LSTM or GRU gate architecture to avoid this long-term memory loss, and also, of course, the vanishing gradient problem. And the LSTM and GRU, all they are modifications of the RNNs where we allow kind of this memory from the beginning to flow, or the data from the beginning, and there are also carefully selected features from the beginning to flow throughout the all the hidden states without being modified by weights and things like that. And it actually ends up allowing us to remember, or allowing the model to remember these things that happened earlier on. So I'll stop there, and I hope you guys learned about backpropagation. Hope this was helpful. Stay tuned for more content. Thank you very much.